So let's get started. I'm going to talk about personalized medicine and how machine learning and big data is really turning that dream into a reality. So this figure up here shows from 1958 until today the increasing number of drugs for a specific kind of cancer called multiple myeloma. So you'll notice that roughly 15 years ago, there really weren't any drugs on the market. Thalidomide, first a drug used for morning sickness for pregnant women, came to market to treat the disease. But really since then, there's been a total of 13 new drugs that have come onto the market. 3 that got FDA approval in the month of December last year. Never happens. 3 cancer drugs coming to market in 1 month. So this is obviously a good thing. New drugs for cancer, new treatment options. This is great. But there is a bit of an issue. These drugs aren't cheap, right? So a lot of these new cancer drugs cost $30K a year, $50K a year, some $100,000 a year. And that's not necessarily bad or wrong, depending on who you're talking to. But, can this keep going? Okay, can we afford it? And this is showing the total amount of spending worldwide across cancer drugs, $79 billion, rheumatoid arthritis drugs, almost $50 billion, diabetes drugs, $41. But that's not really the main issue. I think the bigger issue is what's happening to the total cost of healthcare, both in Canada, the US, and beyond. So the average Canadian family will pay almost $12,000 a year for healthcare. And by the way, in the US, and I get this 3 times a week, most Americans think that all Canadians get healthcare completely for free, right? Which is not quite true. But even in Canada, we're dealing with an increase of more than 50% in healthcare costs from last decade. The US is even worse, where 18% of the GDP, or $2.7 trillion, that's trillion with a T, is spent on healthcare. So that's a lot. And if you look at the curve, the red curve, right here, it's been going just up and up and up and up. And maybe Obamacare is the secret that fixes all of this, but yet to be seen. Okay. But when you combine this fact, this data, with the fact that the US ranks 37th in the world in health outcomes, you really start to see a problem, all right? So we're spending twice as much per capita as any other developed nation, but yet total health outcomes are poor, 37th in the world. So you're paying more and getting less. What does that mean? What are the implications of that? Okay, I'm going to take a step back and see if we can learn something from the world of retail. So does anyone know who John Wanamaker is? Has anyone heard of him? Show of hands. So a few people. So well-known retailer, the precursor to Macy's was Wanamaker's. And one of the things he's well known for saying is that half the money I spend on advertising is wasted. The trouble is I don't know which half. So about 7 years ago, I was involved in creating the first healthcare big data conference with Tim O'Reilly and the folks in California at O'Reilly Media. We wrote a paper called Solving the Wanamaker Problem for Healthcare. And one of the main mantras was really, for the past several decades, we've treated patients as some sort of hypothetical average patient. And that just doesn't work. So you see the analogy to the Wanamaker problem. Right? Which drugs, which health interventions, which surgeries work for which people? Because we're not all the same. Tim O'Reilly, by the way, is the person who coined the term big data back about 8-9 years ago. Here's a slide Just showing data. This is from the Personalized Medicine Coalition. It's showing the percentage of patients in specific diseases that do not respond to a given drug in that class. So for asthma drugs, it says that 40% of patients don't respond to a given asthma drug on average. Diabetes, 43% don't respond. Arthritis, even worse, 50%. So half the people don't respond on average to any one of the specific rheumatoid arthritis drugs. Cancer, even worse, 3 to 4 times you're getting it wrong. So what's going on here? Because we're talking about FDA-approved drugs that are fully reimbursed by insurance that are getting increasingly expensive, and more than half the times they don't work. And this is not to pick on drugs. Drugs are good, right? Right? And they're held to a higher standard of evidence compared to other health interventions like doctor visits or surgeries. So if half the time that we're prescribing a drug, it's not the right drug for the right patient, that means we're not only delivering poorer health outcomes than we otherwise should, including a lot of people dying faster than they should. We're also spending a lot of money that's ultimately wasted. And what did I say the total healthcare spending was in the US? $2.7 trillion. So are we wasting $1 trillion simply because of knowledge blind spots, simply because we don't know ahead of time what treatments work the best for given patients? Right now we have a system where people are treated as some sort of guinea pig or a petri dish. You have standard of care for the hypothetical average patient, and if drug number 1 doesn't work, you move on to drug number 2 and number 3 and number 4. We think there might be a better way of doing this. Before we get there, why is it that we have this kind of variation in drug response or in response to healthcare interventions? Any guesses?
Genetic, right? If you have something that is 95% effective, that means it's 100% effective in 95% of the population based on genetics.
Very good. That is essentially the right answer. Right? We don't always need to go to the genetic level to figure that out, but we are different for a reason, right? We're different down to the DNA. And so this slide here, it's from a professor at Johns Hopkins named Bert Vogelstein, so one of the early studies applying next-generation DNA sequencing to tumor biopsies. And this was from, I believe it was lung cancer patients. And this is just showing 22 patients. And on the left, you see P53, MDM2, a set of key cancer genes, and looking at which ones are deleted, mutated, or amplified across these 22 different patients. And the first thing that strikes you when you look at this is you barely have any 2 patients that have the same set of things wrong with them at the genetic level. Okay, well that's interesting. Because if this is the kind of variation we have in diseases that are classified together and that are treated in the same way, then it's kind of lunacy in a way. It might have been the best we could do, but it's equivalent to having a radio repair shop, and regardless of how or why someone broke the radio, you try to fix it in the same way every time. You slap on a new antenna regardless of what the problem is, right? That doesn't make any sense. And so we know at the underlying molecular and genetic levels, these diseases are all different. So once again, what do we do about it? So I'm going to talk about, well, why now? Why is it that myself and others believe that something can be done about this problem now? Why GNS? Why did we start a company to take this on? And why a company and not academic research or government stuff? And I'll talk a little about the pipeline of computer models that we've been making from increasing quantities of patient data. computer models in Huntington's disease, multiple myeloma, Parkinson's, various other cancers, diabetes, and what have you. And specific examples, including preterm birth. Then I'm going to end with just extrapolating from where we are today and really looking at the question of, well, what happens if we win? And when I say we, I'm referring to GNS, but I'm actually not just referring to GNS. I'm talking about all of us together as a society. What if this all works? What if data-driven medicine goes from being a dream to a reality? How does it change every one of us? I don't think there's anybody here who hasn't been touched personally by really a deadly illness in their family or themselves. And if it hasn't happened yet, it's coming. So why now? What's been changing? What's enabled this great opportunity? So there's a lot of health data. So the traditional health data sources are things like claims. So medical and pharmacy claims. So every time a drug is prescribed or a procedure is done at a hospital, there's a claim. There's a claim form that the doctor or the hospital submits to the health insurance company or the government, and they pay it. Or they argue and then they pay it. Right? Lab results. I'm sure most of us in the room have had some lab work done in the last couple of years. Family history, what does that tell us? Demographics. Okay, so this is the usual stuff, the traditional stuff. And we certainly have a lot of this in great quantities. But part of this big data revolution has been driven by more exotic kinds of data. The Human Genome Project, so that's a picture of Craig Venter and Francis Collins, who's the head of the NIH. So these are the two gentlemen who led the Human Genome Project. So back in 2001, they announced completion of it, the first ever decoding of the Book of Life. Took 11 years, cost $3 billion, and it gave rise to the knowledge of the underlying stuff that we're made out of and the underlying molecular information that drives disease and even responds to drugs. But of course, at the beginning, one genome is not going to do a lot. So Peter could tell you that. You're not going to do data mining or machine learning from just one genome and learn anything. This only becomes really valuable when you have lots and lots and lots of genomes. And certainly we're not going to do that at $3 billion a pop in 11 years. So the big news here is that it now takes less than a day to get a full human genome and less than $1,000. Massive. It's a huge change. It's a lot of new genomics data. A lot of new wearables. Who here has an Apple Watch or a Fitbit? Okay, so around 25%. Okay, so these are becoming more and more popular, and they're throwing off lots and lots of data. Data exhaust. That's telling us a lot about ourselves in terms of behavior. And then there's electronic medical records. And in the US, there was a lot of money put in to encourage adoption of these systems. Canada was actually further ahead. Okay, so now we have a lot of new data sources, from imaging to consumer behavior. So what things do you buy? Who participates in things? The molecular information, all of this that we can now mash up and put together in a big, big database and potentially learn some new things. In particular, learn what works for whom. But it's not just about the data. What good's having a big pile of data if you don't have the tools to crunch it and discover new knowledge from the data? The data by itself is kind of useless. So part of what's powering up the revolution in big data and the revolution in personalized medicine is the rise in computing power. So this is a figure showing the last several decades of Moore's Law. Moore's Law that predicts the increase in computing power, decreasing size, decreasing cost. And this has been really incredible. It has not slowed down in all these decades. And so we now have access to computing power that's orders of magnitude more powerful than even 5 years ago. at a fraction of the cost. And it's going to keep going. And it's not just Moore's Law, it's also cloud computing, the fact that we have access on demand to networked machines, right? And it doesn't matter where we're located. So our company is in Boston. We run all day, every day on the Amazon cloud. Now, the machines might be in Washington State, just across the border from you here, but they might be somewhere else, and we don't really care, right? But the point is, this has become very easy, very cheap. So it's created, in a way, the perfect challenge or the perfect opportunity. You have a massive increase in the number and cost of interventions, whether they're drugs or surgeries or new robotic techniques. That innovation's great, but we still have to figure out who to apply it to. We also have a huge rise in the amount of data, an exponential increase in the amount of data, and now investments to leverage it. But what's missing? Is this enough? Not quite, right? So machine learning, so this is where the math comes in. Machine learning, running on these very big machines and running this data through them, now gives us the opportunity to learn new knowledge, to create new knowledge. Okay. That's why we started GNS. So this is a picture from 2002. So the person on the right is Dr. Aya Khalil. She was a PhD student in physics at Cornell with me when we were thinking about this crazy idea. And so we started this company in order to really tie these pieces together. We saw where technology was going. We saw where Moore's Law was going. And we really saw where genomics was going. I was doing academic research in the field years before that at the Santa Fe Institute in New Mexico and at McGill in Montreal. And eventually, when the human genome was sequenced, it was clear to us that there was a gap between that data and turning that data into very useful information and powering up personalized medicine. At the time, that was not a popular idea necessarily. So what do we do now? What is GNS Healthcare about? Our mission is the application of machine learning to better help health plans, providers, and pharma companies better match existing and emerging drugs and other health interventions to individual patients to improve outcomes and lower costs, to save hundreds of billions of dollars, as well as discovering new interventions. So that's why we exist. The company was founded in 2000. That was almost 16 years ago. We're 60, almost, I think we're approaching 70 people. Half of those people are PhDs in bioinformatics, systems biology, computer science, epidemiology. And we're known for a particular technology platform called REFS, which is the first of its kind that doesn't just find patterns in data, but it actually attempts to reverse engineer mechanisms from data. Mechanisms such that you can ask what if questions of a system once you've recreated that system on the computer. Now you can do in silico experiments and test out a particular drug in a particular patient and see, well, does that work on that patient versus another drug? Let me stop for just a second. Any questions? I've been talking for a bit.
Hi, my name's Mandy. I'm one of the students in the President's Dream Colloquium. I just have a question about the human element in all of this, and this came up in Dr. Chow White's lecture last week about the lack of people who can actually analyze the data that is coming out and to apply it to healthcare. So how is that being addressed with this?
That's a great question. That's a good advertisement for our company. So a lot of what we've spent the last 15 years and $50 million doing and developing is scaling this refs technology. And I'll get into how the refs technology works, but the key aspect of it is that it's automated in terms of turning data into computer models. And that automation is really, really important because as the data keeps getting bigger and more multi-layered, and you're dealing with genomic data and electronic medical record data from hundreds of thousands of patients or even millions or tens of millions of patients, this is not something you can do manually. It's not something you can do with an Excel spreadsheet and an individual researcher doing their analysis, or it's not something you can do with SAS, which is a well-known company in the US. I'm sure they would take offense to me throwing them under the bus, but when you get to data of this scale, and not just in terms of the quantity of data, but the complexity of the interactions that underlie the data, you need really a different kind of technology. And that technology needs to scale. And that's a key part of how you get around the issue of there not being enough trained PhD data scientists or modelers. And I like to separate those two things out because data scientists in our parlance means the people who do the data munging. They assemble the data into the databases, and which is a really important role. You need to do it, but it's different than the machine learning folks who do the modeling and apply the fancy algorithms to the data. Another question?
This might come with the technical part that you're going to talk about, but I guess cancer data in particular is so heterogeneous, so your models must evolve. Is that part of the technical pipeline? Because you can't obviously apply a similar model between subtypes of cancer, let alone, different cancers.
Yeah, great question. So in particular, the cancer genome in a given tumor in a given patient is evolving over time. And of course, it's even evading treatment. And so one often has a need for repeat biopsies and so on and so forth. And I think one of the reasons why blood cancers have been more successfully treated lately is the fact you can get repeated biopsies. So our system does keep on learning. So as new data is generated, that gets fed back into the system, and the system learns and gets smarter and smarter as it goes along. But then the other aspect of your question, it really gets to the personalization of it. So, models can only be made from a large group of people. Like we can't take your data and just make a model of it because we actually need the natural variation between all the individuals. So if we wanted to make a model of say diabetes based on patients in the greater Vancouver area, we would depend very much on the variation in patient backgrounds and the variation in what treatments they're using. And what gets reverse engineered are models that can now apply patient by patient by loading in the specific input data from a given individual. So in that way, the models become personalized, and that's why you can apply a given model to different patients at different points in time. Yes, absolutely. And I will get into a little bit more of that. So just back to the background of our company. So who are we and where do we fit into the world of things? So we're considered to be thought leaders somewhat in the precision medicine space. Here's just some recent press. The co-founder, Aya Khalil, is named as one of the most inspiring people by Pharma Voice. I am a co-author of what's considered to be the first publication in precision medicine. That was in 2009. Last summer, I had the honor, it was an honor, to speak right before Bill Clinton at the annual health insurance meeting. And just last Friday, or a couple Fridays ago, I was on CNBC on Squawk Box regarding an article in the Wall Street Journal regarding the employers mining data from their employees to figure out who's going to get sick and whatnot. And it was an interesting interview because they really came at it from the angle of employers must be doing something bad. And we were involved here because of an early computer model we made with Aetna around metabolic syndrome, which I'm going to talk about a little later. And when the Precision Medicine Initiative was kicked off last year by President Obama, I happened to be invited to the meeting, and they sat me in the front row. And so GNS has been a part of the revolution in precision medicine for some time. And we're looking forward to hopefully it continuing after he's not in office. But we'll see. And here's just a handful of our partners. And the notable thing here is that we work with entities really across the spectrum, from biotech and pharma companies like Pfizer and Celgene to patient foundations like the Multiple Myeloma Research Foundation and the Cure Huntington's Disease Initiative, Regents Blue Cross Blue Shield that covers patients across Washington State, Oregon, Utah, Idaho. They're the world's first health insurance company. Okay, and playing across the spectrum of healthcare is very important, and I'll come back to why that's important when we get to some of the specific applications and data that we use. Okay. So the machine learning. What are the different types of data analytics and machine learning? Because I'm sure people are talking about big data all the time. And well, what does it mean, and what are the differences? So this pyramid comes from a guy named Tom Davenport, who's a professor at Babson College in Boston, and he's the author of one of the early books in the space called Competing on Analytics that focused on various industries where companies were gaining a competitive advantage by using data analytics. This book was published 15 years ago, so he was ahead of the big data curve. And what he described is this hierarchy of data analytics, from standard reports on the bottom of the pyramid that answer the question of, well, what happened? To statistical analysis, why is this happening? So drilling down into the details. To forecasting, what if these trends continue? What if the temperatures keep on rising in British Columbia? Predictive modeling, what's going to happen next? And a lot of people think that predictive modeling is the be-all, end-all of data analytics and machine learning and such, but it's not. Because really, what's the point of predicting the future if you can't change it? We don't want to just be able to predict the future, regardless of whether you work on Wall Street or Bay Street, or you coach a basketball team, or if you run a manufacturing plant, or if you run a country. You want to be able to, you're trying to make decisions. If you run a company, you're trying to make decisions all day, every day. What if I do this versus that? And of course, we don't have the luxury of following all the different pathways and seeing the result. But what if we could do that computationally? What if we could infer the mechanisms and on the computer test out many what-if situations? Then you could see, well, what's leading to the best result? Out of the 10 different choices I have in front of me, what's leading to the best result? And that's what the top of this pyramid is about, optimization and inference. What will happen if I do this? So you're not just trying to predict the future. You're not just trying to extrapolate and see what's going to happen next. You're trying to see what's going to happen next under many, many different scenarios, many different interventions, because then you get to see all of the different pathways. And so I think the application to healthcare and drugs is somewhat obvious. If you're a cancer patient and you're dying of a particular form of cancer, you want to know, out of the 10 drugs that are either on the market in your disease or not on the market, which one is going to have the greatest impact on shrinking your tumor and extending your life? That's the question. You don't want to just know what the statistics are in terms of what's going to happen to you. You don't want to know, what action do I do next to drive to a better result? So what powers that up is a different kind of data analytics, a different kind of machine learning than what is really on the cutting edge today. And for us, that comes in the form of technology called refs. So we aggregate lots and lots of data, or we buy it from people and companies that have aggregated it. Like on the pharmacy and medical claim side, we've been licensed 100 million lives worth of data with roughly 3 years of history. So every medical claim, every pharmacy claim, so every drug, every dose, with linked labs and demographics and use of durable medical equipment. electronic medical record data in the hundreds of thousands and the millions, clinical trial data, and then genomic data and even mobile health data. And we attempt to mash this all up and connect these different data layers together into unified data frames, or data lakes, as some people like to call them. Then this data gets entered into a specialized warehouse we've developed, and then it goes into the REFS platform. So the REFS platform is the machine learning platform, machine learning and simulation. It really is a marriage of techniques and ideas that come from both computer science, which is where artificial intelligence comes from, and modeling and simulation, which really comes out of physics, applied math, engineering. And what it does, and why it's called REFS, is the RE is reverse engineering. So from big piles of data, imagine you have a big spreadsheet full of data representing different patients. The first step is the reverse engineering of networks, of relationships from that data. That's where the RE part comes from. Then the forward simulation part comes after you have the ensemble of network models. So this REFS platform is running on the cloud. This runs every day, all day, every day, on tens of thousands of machines to now reverse engineer network models like this that connect interventions, like a drug or a behavioral intervention, to the patient characteristics, both demographics, as well as other background variables such as genetics, things that don't change, to those process variables that do move, like your lab values, like even genomic changes, in order to predict both clinical outcomes and financial outcomes. So our system is reverse engineering many trillions of hypothetical network model structures to boil out 1,000 or so of the most predictive, of the most accurate representations of the system that gave rise to the data. Once we're able to make computer models like this, or ensembles of them, we're now able to ask and pose questions to the computer model, such as, does intervention Y, imagine it's a particular drug, improve the outcomes and lower the total cost of care for patient X? So how do we do that? Assume that we can make these models from a large cohort of patients and that these models are accurate. Then we get data from a given individual. Let's say this model needs to be driven by genomic data from someone's blood. Right? So we would take a blood sample from Peter, or my brother. We would run it through a molecular profiling machine to generate the data. Then we'd enter it into this model. And then we would say, okay, what if we apply drug X to this representation of Peter? What happens over here? Does it move the clinical endpoint of the disease we're trying to treat, or does it not? Then we repeat it again for the other drug we have at our disposal, and the other drug.
Quickly. So the readout for your model, for your simulations, it's in silico only?
It's
biological phenomena?
It starts off as in silico, but driven by lots and lots of wet lab data. That's how the models get made. And then the models get validated, once again, with wet lab experiments to validate, well, is it correct? So if the model is predicting that a certain knockdown is going to cause tumors to shrink, does that actually bear out in reality? And if not, that data becomes a useful input back into the system, which relates to your earlier question.
Is that for individuals or just for validating your models?
Do we do it to benefit individuals, or do we do it just...
Run it in cells. Is it in cells or in vivo as well?
Both. Yeah, we do a lot.
Is that for an individual?
Yes.
For testing, or just to validate models in general?
So we don't sell directly to consumers. We've had some patients approach us in specific disease areas because we've had press releases go out, for example, in multiple myeloma, the creation of the world's largest computer model of multiple myeloma from the world's biggest data set, and that was together with the Multiple Myeloma Research Foundation. And we don't think we're going to turn into a direct-to-consumer company. The regulations are very different for that, and so on and so forth. But ultimately, it's for individual patients that this is all being done, and we need that data from individual patients at the end of the day, whether it's a clinical trial or an observational study, to go back and validate, did it work, did it not, and what are the models missing in order to get better and better. So. Any other questions? Please.
Did you know from each patient, right?
Is the genome for each patient like has to be fit in this machine learning technique, or if I just show up with my name, it's like I have this disease, does your model without giving my genome to your company will know if the drug will work or not?
So it depends on the disease, and it depends on what the model is constructed with. So for example, 2 weeks ago, we put out a press release together with Pfizer, a large American pharmaceutical company, on a computer model in type 2 diabetes and new discoveries that came from that. And that model was made entirely from electronic medical record data. There was no genomics data in there. So in that case, we would need some elements that are specific to you, but not necessarily genomic, right? And diabetes is one of those diseases that it's not purely a genetic disease. For cancers, we know that it's genetic mutations and deletions that drive cancers. So in that case, we would need the genetic data. So it really depends on the nature of the model, the nature of the disease, but we would need some specific information about you.
Short question.
Very short question. I'm just thinking about, again, what came up in last week's lecture, which what's happening in POG, where
Happening where?
in maybe Dr. Chow White can say a bit more about it.
Oh yeah, sure. Yeah.
And I'm just thinking about how in a day for $1,000 you get the genomic information, and now GNS is automating looking at all that data analysis. So is there something that's going to happen in the future between the two, with GNS and with POG, helping doctors look at patients and help drive the healthcare?
That's a great question. We're going to be having a lot more discussion with entities in British Columbia going forward. We don't have any sort of deal in place yet. I've met Marco, Amara, and folks over at the Cancer Center. And our company has a great interest in having more of a presence in the Pacific Northwest broadly. We do a lot of business across the border, and as a Canadian who still has a lot of family in Canada, I have great interest in seeing some of these innovations happening north of the border. And I feel like Canada needs to do more in really investing in cutting edge technology, but also the commercialization of it and the translation of it to the real world. And more entrepreneurial stuff happening as a result. So if we can help do that, that would be great.
Were you listening to us talking at lunch? Is that what happened there? So we got one more.
Well, the $1,000 genome has come up a couple times, and I tried not to bring it up. I feel like the old guy in the bus, who's kind of scribbling, and if they only listen to me and stuff. But I mean, there's like 10% of the human genome that is really complicated, has a lot of variability that these high throughput techniques don't genotype very well. And I think that's something that just gets lost in this $1,000 genome. You hit 90% of the commonly known polymorphisms, but a lot of immunoglobulin, T-cell receptors, MHC, really important genes that still need to be looked at.
Yeah, I agree. So I went to grad school at Cornell, and one of my friends, we actually TA'd a class together, is the founder of a company called Pacific Biosciences, which really specializes in the deeper sequencing and such. So they actually were incubated in our office in Ithaca, New York for 2 years because Steve couldn't afford to do it at any other place. And so we have great interest in those deeper sequencing techniques. So I agree with you. It's not, what gets advertised is is good, but it's still going to be a while until it fully gets there. And I think there's also a question about the price. A lot of people extrapolate to, well, it's $1,000 now. When is it going to be $100? But I think there's a lot of things potentially keeping the price from dropping another order of magnitude.
So the question about the algorithms that they use for machine learning, based on the picture here, I would guess that's a neural network. But do you use like different models depending on depending on disease and depending on the data that is coming in? So basically, like, is it neural network as shown here, or is it like different?
Yeah, so it's different than neural network techniques. So, artificial neural networks really try to map a system onto kind of a representation it's not trying to get at the mechanisms of the system. It's trying to just map a system onto, an artificial view of how our brain works, essentially. So what we actually use is Bayesian network inference combined with global optimization is the technique. And it's causal inference was really pioneered by Judea Pearl at UCLA, first in the field of robotics. He won the Turing Prize, I think, just a few years ago. But the other part of your question is it the same model? Is it the same parameters or the same technology used each time? So it's the same refs platform that's used again and again in all these different models and all these different types of data. But what does change are sometimes the choice of the potential input of the actual mathematical forms. And so to not go into too much math here, I promise there won't be any equations, but here are the three basic steps of how refs work. So it starts off with enumeration of the building blocks of, from the data. So this is now enumerating many different ways that the variables can interact together, whether it's genes, proteins, or EMR variables, or what have you, or demographic variables. And those little squigglies are representing the mathematical functions that relate the components together. And so step one is generating, imagine that this is like just like regression on steroids. And you generate trillions and trillions of these building blocks, and you create a big bucket of jigsaw puzzle pieces. That's step one. And you have p-values that indicate how statistically significant those are. Then step two is the machine comes along and puts its arm in this big bucket of jigsaw puzzle pieces, and it attempts to solve the jigsaw puzzle. And it tries it once, twice, but actually is doing this 10,000 times, in parallel, and then trying to converge on the answer. And that's this step two. And this is the hardest part of the process. So this is what needs the really big iron, the big supercomputing, because this is an NP-hard problem for those computer science geeks in the room. So it's non-polynomial, so the size of this grows exponentially, which means that when you're dealing with systems that have hundreds or thousands or millions of variables like a genomic system, you're dealing with an astronomically large number of possible network structures, like 10 to the 347, right? So there's no way to exhaustively solve this, and so the core of our technology are clever ways of approximating that search through network space. And once that's done and it's converged, now you get to do the fun step of now simulating those what-if questions into the system. Now you can say, what if I knock out gene A across all the different 1,000 models in the ensemble? How does it change the outcome? If the outcome is, say, progression-free survival, or it's size of tumor, or an endpoint for multiple sclerosis. And then you get to run these simulations in a really high throughput way really quickly. But that's actually at the core what it's doing. And this is why you need mechanism. This is why patterns aren't enough, because with just finding a correlation, with a correlation you can't say, well, what if I change the price of oil? How does that change the price of gold? You can't do that, because all you found is a correlation. When you have mechanism, you can now say, what if I change this variable? What happens down here? And what happens down there? So that's the core of it, and that's also in some ways how it's different than an artificial neural network.
Here, we're not used to this
That's
kind of
great.
thing, but
Hi, I'm a population health scientist. I see your logo down there says population health personalized. And I had two questions related to population health in this. The first is, best estimates, 75% of our health is determined by things outside of healthcare. So how does that fit into this? And the other is an ethical question about, it's incredible, really incredible, but how does this address population health and health inequities without exacerbating them? Because I'm originally a U.S. citizen. Now I work in healthcare in Canada. Very different perspectives on healthcare. Very different care that you receive depending on where you are. And I can see this as making great improvements for a subset of the population, while others are left behind.
It's a great question, both of them, and we're sort of living mirrored lives, right? I'm a Canadian living in the U.S. and you're American living up here. So the second question is really about how do we make sure that this doesn't just help the 1% become healthier, live longer, create greater disparities in healthcare? And that's really a big deal. It's a great question. And that's been some of the argument against or in the context of personalized medicine has been, well, wait a sec, you're talking about using expensive DNA profiling techniques to figure out which of very expensive drugs to apply to extend life by another, sometimes only 6 months or 10 months. Is that really the best way to spend our money? And then you get to, well, whose money is it and all that. And in Canada, we accept a socialized healthcare system. Rightly or wrongly, we accept it, we live with it. We don't have a lot of drugs and other things advertised here, so I feel like we don't know better a lot of the times. And in the US, it's not a socialized healthcare system. There's certain people who want to turn it into that, and it's partly socialized. Put the political rhetoric on the side. Half of healthcare spending in the US is from the government. Medicare, Medicaid. So Medicare is for older people, past 65. Medicaid is for poor people. Then you have the VA. So you already have the US government paying for half of healthcare. And you have employers paying for a lot of the rest. So it's, and even when Obamacare was being introduced, you had people protesting and saying things like, get the government's hands off my Medicare, right? And it's been there for so long, people don't even know it's the government anymore. So back to your question, how does this become something that kind of makes all boats rise versus just those who can afford it? And I think it goes back to what I was getting at the beginning, which is, if we are wasting $500 billion a year in the US on health interventions that just simply don't work for the given individual. It's not that they're bad health interventions, they might be great, but they're mismatched to the individuals. And this isn't a question of aligning financial interests like Obamacare tries to do. This is a question of knowledge blind spots. And so if you could take out $500 billion of just cost, what does that do to improve health outcomes across the board, especially for even those who are less fortunate? One of the things that doesn't happen in the US as much as it does here is primary care. There's not enough spent on preventative medicine. One of the examples I'm going to talk about is metabolic syndrome, because it's one of those true kind of pop health problems, and people normally don't think about personalized medicine and population health together, but they really are one and the same. And then I think your first question, if you can just repeat that again.
Best estimates that 75% of our health
is great.
Determined outside of healthcare.
Yep. Great question and point. So, the built environment has so much to do with healthcare, and I'm always struck by the stories I hear about efforts to change healthcare and health outcomes, but in environments that are very different really across the board. And so, to the extent possible, we're using a lot of geocoded data to capture the environment down to the zip code and even those 3 extra numbers on the zip code that get down to the neighborhood. Because it very much is telling of what you're exposed to. And the wife of one of of our employees, the wife of our chief mathematics officer, she's actually focused on exactly this and has a big federal grant for studying the impact of the built environment on health outcomes. One of the stories that comes to mind when you bring that up is we worked with the former chief marketing officer of Medco, one of the very large pharmacy benefit managers in the US. And they were trying to improve their marketing story. This was a company that buys drugs on behalf of 60 million Americans. It doesn't exist in its current form. It's now part of Express Scripts, which is the biggest drug buyer in the US. And I remember this person, telling me about an epiphany he had. This guy is from Detroit, and his younger brother called him up, who still lives in Detroit, and he said, "Jack, I have diabetes, and I need your help." And he said, "Well, the first thing is, what is salmon?" And Jack was like struck. How could he not know what salmon is? But he lives in downtown Detroit, and what there is, a lot of Kentucky Fried Chicken places, a lot of liquor stores. He's surrounded by bad stuff. I mean, it's the truth. I mean, the disparities are massive, and I think it's much more so in the US, I think, than in Canada. And I was telling someone the other day, so I live in Cambridge, and I'm fortunate enough to live in a really nice neighborhood. I can't find a McDonald's or a Kentucky Fried Chicken if I wanted to cheat and do something like that. And so the environment plays a huge role in health outcomes. It plays a huge role in medication adherence. So one of the programs we have running in Washington State and Oregon is in medication adherence. And the consumer buying behavior data ends up being really predictive of who is going to take their meds on time. It's huge. And so it's a long answer to your question, is to say you're absolutely on point. We do a lot to get that data outside of the fancy genomic stuff. And that's, I think, different than a lot of companies in precision medicine that really focus on the genomic piece. I'd say 7 years ago, when we were pulled into the broader world of healthcare, we really start to see that front and center. We still do a lot of things with genomic data, and I don't think it's a matter of saying, well, genomic data is good for this, and environmental data is good or bad for this. We want all of it, because all of it can be very informative, not just of treatment response, but also engagement. Engagement's huge, because a lot of the diseases we're dealing with are lifestyle diseases. Okay, great questions. Okay, so let's actually get to some examples of, well, how is this actually being used in practice? So these causal models really drive impact in 4 different buckets. One is care management. So these are health insurance companies, hospitals who take care of patients. So for drug comparative effectiveness, which is the best rheumatoid arthritis drug for a given individual? How do I best utilize my healthcare resources? Pharma, health economics and outcomes research, really similar. Drug comparative effectiveness and drug progression. Biomarker discovery, models that stratify patients in clinical trials. And then also models that uncover new intervention pathways, new drug targets, new treatments for cancer. And we have an increasing pipeline of these computer models across a number of diseases, from cardiovascular and metabolic diseases like type 2 diabetes, oncology, breast cancer, colon cancer, autoimmune diseases like rheumatoid arthritis and psoriasis, neurological disorders, multiple sclerosis, Alzheimer's, Huntington's, and several others. I'm going to, and we should just do a time check because I have a few examples here, but I think we might only have time for 1 or 2. So this is a collaboration with a company called Global Genomics Group, or G3, and they've really pioneered new ways of analyzing and imaging the heart. Okay, so there's 75 patients enrolled in this study. So this is 22 trillion data points have been collected so far. And our REFS technology was applied to now recreate, to reverse engineer the most comprehensive networks, the most detailed networks of human biology that have ever been done. Okay? and used for discovering new drug targets, new biomarkers, and ultimately better ways of matching drugs to patients. So the phenotyping was done with a novel imaging technique that they have patented, and simultaneously whole genome sequencing was applied along with whole transcriptome sequencing, proteome profiling, and metabolome and lipidome. So this is one of the most comprehensive multi-layer studies ever done, and done very carefully. So here are all the different layers of data that were used. So 103 different variables ended up making it into the model-making machine. 9 million causal assertions, those network fragments, those jigsaw puzzle pieces I told you about. So from this data, network models were recreated, connecting the DNA sequence variation and clinical parameters to the various process variables in order to predict plaque driving coronary artery disease. And here's just a spaghetti picture of some of what came out, and what you can see is the actual outcomes in red that are connected to various other components like various proteins and mRNA and other things driving the outcomes. Now, these labels are missing on purpose because some of these discoveries are being patented as we speak. But what I can tell you about the specifics of what was discovered is that the model recapitulated all the known causal, genetic, and molecular networks driving CAD. So it recovered the key LDL pathways, right? The key cholesterol pathways that were discovered decades ago, and also discovered a particular gene called PCSK9, which is the target of several drugs that have just come to market. And so in the course of 10 months, with just data and the computational technology, we've recreated 70 years of cardiovascular disease biology in just a fraction of the time, and straight from data. So this is not expert knowledge being put into the models or seeding the models. This is now the machines discovering this knowledge straight from data. That's the really notable thing here. And keep in mind, the data is getting better, the machines are getting bigger, they're getting cheaper, and this is starting to now drive biological and biomedical discovery in a way that was just not possible before 10 years ago. And here are some of the other areas it's being applied to: osteoporosis, type 2 diabetes, and such. I'm going to switch to another example. Anyone here familiar with the problem of preterm birth? Babies ending up in the NICU? Okay. So the challenge is 11% of expectant mothers end up delivering prematurely. This is a really bad thing. So 10,000 babies die every year as a result in North America, and those that survive have a whole host of health issues. So the question is, can we predict ahead of time which of the 11% of mothers who deliver prematurely are going to do that, such that we can intervene and attach the right interventions ahead of time? Okay. And this is a multi-billion-dollar a year problem. And it's even worse in countries outside of North America. So the question is, which interventions for which patients at which time? Here are the typical set of interventions, from progesterone to bed rest to smoking cessation, that are applied at different times. And the challenge is, who's going to have a preterm birth? And where's the signal? Is it in the genetics? Is it in something else? And there's a number of efforts to predict this in the past, and what we've seen is that the state-of-the-art isn't enough. The predictive power of these models and their applicability has not been strong enough to actually really lead to a change in population health. And so, together with the Inova hospital system in the greater DC area, we embarked on an effort to now collect the most comprehensive data from a cohort of patients that's ever been done. And this was from roughly 2,500 individuals, mother, father, baby, full genome sequencing, gene expression, the electronic health record data. And then our company made a whole series of models of the different layers, both alone and together, to now generate a system that's now predictive based on, at the beginning, just baseline questions from the EMR. 6 questions I can run on an iPad that now generate a risk profile. So for this individual, it says they're in the 46th percentile. So it says that this patient has high risk. This now triggers a blood test being drawn that's going to be profiled for the 7 genes that were discovered to determine if that risk is really high, or it's extreme, or if it's moderate. And then particular interventions attached, like progesterone or bed rest. So this is a program that's now being validated at a couple of centers that's going to be kicking off this year. And the type of return on investment is huge, both in terms of money, but also really the human cost. So Peter, I'll go with your guidance here. I have a 3-minute, 4-minute part at the very end. I could skip to now if we're running short on time, or I could go through this one last example in metabolic syndrome that's running with Aetna.
So, yeah, we'd like to have maybe 5 or 10 minutes for questions, and so we have about 15 minutes.
Okay, I'll run through this quickly. Okay. So this is an effort. So does anyone here know what metabolic syndrome is? Oh, of course. Well, you can't answer. Okay. In the interest of time, I will just tell everybody what it is. It's essentially prediabetes. It is having 3 or more of these clinical risk factors being out of range. So waist size, blood pressure, triglycerides, HDL cholesterol, or blood glucose. If 3 or more of those are out of range, it means you have metabolic syndrome. And if you have metabolic syndrome, you're 5 times more likely to develop diabetes and 2 times more likely to develop cardiovascular disease. So the question is, can you predict ahead of time who's going to develop metabolic syndrome out of a group of so-called normal people? So together with Aetna, which is the 2nd largest health insurance company in the world, we went about turning large quantities of data from a very large self-insured employer, using our technology into computer models that could predict which individuals are the most likely to develop metabolic syndrome in the next 12 months, down to the specific risk factor, and then match to a specific intervention that's going to reduce their risk. So the data that was fed into this was from roughly 36,000 individuals, so 18 million claims events. So it was demographics data, preventative visits, health risk assessment data, participation in wellness programs, disease management program participation, biometric screening, and medication adherence. So all these different types of data were used together to make 2 different models. The first model, what we call the velocity model, attempts to predict the change in metabolic syndrome status 12 months forward. Okay. The predictive power that came out of this was 0.88. So area under the curve means it's a measure of predictive power. It doesn't exactly translate into 88% predictive, but 0.88 is pretty good. Okay. Turns out when we actually just drive the models with just claims data, we get a predictive accuracy that's not quite as good, but it's still pretty good, 0.80. So without even doing the biometrics. And so this is what it looks like for a given individual. So this is really this concept of mass personalization. This is a population health problem, but it's being personalized, even though there's no genomics involved. Right? So this is saying, what's the probability of each of these factors being out of range in the next year? So this says there's almost 60% chance that this person's waist size is going to be out of range. and a 37% chance their blood pressure is going to be out of range, and then the other factors being lower. And the reason why it's a curve and not just a point is because, remember, there's a whole ensemble of models that are getting to vote. Okay? So this tells us that for this individual, it's their waist that we need to pay attention to. Okay. So how do we use this? What's the net benefit of this? So 2 individuals, you're trying to figure out where do you put your precious healthcare dollars? Who do you call, and what are you calling them about? So we have one individual here who has 2 risk factors of waist and HDL, and their next highest risk factor is glucose. And so this person's overall probability of developing metabolic syndrome next year is 92%, versus this other person, a male age 37, who has HDL and triglycerides as the risk factors. And glucose is the next highest add, and his probability of developing metabolic syndrome next year is 40%. So this allows us, or allows Aetna and their self-insured employers to prioritize who they're targeting the resources to. So who to call out of all the normal people, and what are you calling them about? Because if you just tell people, eat your greens, don't smoke, don't drink, people just don't do that so well. But as soon as you get it to be more personalized, it now can be more targeted in terms of which interventions are being attached. Okay? And then, because these models are causal, you can now ask the what-if questions. The what if we increase the level of medication adherence in these individuals? What's the impact on their chances of developing metabolic syndrome? And this is showing a reduction and a distribution of that. And then similarly, the impact of preventative visits. If we now intervene by increasing the number of physical exams that are done, what impact does that have? And it has roughly about a 10% impact. Kind of surprising, even for the cardiologist lead from Aetna we worked with. So that's just an example of the same kind of framework, different kind of data, different kind of problem, but being applied to personalized care, person by person. Okay. Now I'm going to end with just kind of dreaming a bit, thinking a bit further ahead. So what happens, this says if GNS wins, but it's really if we win, and by we I mean you and me and everyone else. What happens if this dream of personalized medicine comes true? This is a figure we like to use that is really showing a treatment landscape. So if the vertical axis is effectiveness, and this other axis here is patient characteristics. Of course, this is a multidimensional vector we're projecting down to just one axis. And then here are all the different drugs for a disease like rheumatoid arthritis. If we had computer models from a sufficient quantity of data, it would tell us that, okay, this particular drug, Humira, works really well in patients that look like this, whether that's a genetic or a demographic type of characteristic, versus patients that look like this. So people like this shouldn't take that drug, but people like that should. We're getting to the point where we're having sufficient data and sufficient technology to, in essence, turn the lights on and show us what works for whom. And if this all works, what does it mean? What does it mean to each of you? What does it mean to me? So, relatively recently, our family went through a scare with my dad. So he was diagnosed at age 69 with very advanced prostate cancer. Turns out people of African descent have a higher chance of it, and I think people with specifically Caribbean descent have a higher chance of developing it. And so at age 69, I got that phone call, the phone call we all dread. This is a picture, by the way, of my dad, my mom, and me somewhere in New York. I used to write a blog for Forbes some years ago called Healthcare 2020. And so here I was faced with this question of all this big data stuff I've been doing, can it save my dad from cancer? Okay. So in this case, we got lucky and standard of care worked for my dad. Okay. We did go about getting his tumor biopsy sequenced and such in case it didn't work. And luckily it did work because we didn't find anything that was going to point to a new other treatment. Here's a picture of Stuart Kaufman, who was my mentor, my pretend adopted father, and Elizabeth Kaufman, his wife, my pretend adopted mother. And so roughly a year after the scare with my dad, once again, another call came. Now, Stu is an MD. He is really the father of systems biology. He's one of the fathers of math biology and a co-founder of the Santa Fe Institute. And Elizabeth was diagnosed with pancreatic cancer about a year after my dad. And despite all the tools we had at our disposal, Stu's background, and one of Stu's close friends named Lee Hood, who is the inventor of automated DNA sequencing, we couldn't save her. Right around that time, we were dealing with yet another family member getting sick, and that's our cousin, TD Hill. And this is a picture in Ottawa in the hospital probably 3 weeks before she passed away. She was 43 years old. And once again, that call came, and given what I do for a living and what I've spent the last 16, 20 years of my life doing, technically I should be able to do something to help. And despite the calls made to the head of the National Cancer Institute and the president of MD Anderson and Foundation Medicine and such, it was too little too late. We lost TD at age 43. So at a certain point, I got tired of these phone calls. Tired of not being able to do anything with all this great technology being applied on an industrial scale and so on and so forth, but then when that phone call comes and you need to deliver, we weren't able to. So a few of us got together to say, enough is enough. If we can't do this, if we weren't able to save Liz and my cousin and others, then and who can? So we created something called TMED, Transforming Medicine, the Elizabeth Kaufman Institute. And the mission is to really accelerate the scientific evidence at the core of personalized medicine. So it's not really that different from the mission of GNS, except it's a pure play, not-for-profit, focused on simply saving patients by generating this data. And the co-founders are Stu Kaufman, of course, my mentor. Lee Hood, a much younger picture of him. For those of you who know him, Lee Hood is really the father of modern biotechnology. He's a co-founder of Amgen and the inventor of automated DNA sequencing. He's just over the border there in Seattle. And Kathleen O'Connell, who is the producer for 48 Hours on CBS, who lost her son, a teenage son, to glioblastoma, a form of brain cancer. And Bob Goldberg, who runs the Center for Medicine in the Public Interest. So we started this not-for-profit to really turn the tide. And we think we can do it. And we are certainly looking for others to join us. And that's how I'd like to end my talk, is really based on how all this big data and machine learning can impact us. So thank you very much, and thank you for great engagement and great questions.
Honor, actually, to bring this to a conclusion and to say, Colin, this has without a doubt been one of the most concise, I think, compelling, really compassionate kind of presentations we've had in this room, and you really give the shape of the future to big data in a way that I think is really commanding us all to think about it and take the responsibilities more seriously. I cannot be happier to introduce the two students responsible in our colloquium for hosting you tonight, and to actually turn over to them the responsibilities for both a final question, maybe one from the audience, and the presentation, which may surprise you and will be perfect for TMed. I can tell you that.
Catherine, so one thing I have to be the kind of ogre of is time here. We've got about 10 minutes at the max before we need to be done. So, okay, thanks.
Just first, then.
Sure. Thank you for your talk. It was very insightful. One of the points you brought up repeatedly throughout the discussion was sort of the data quantity needed for these models. You spoke of how obviously this data is useless without the technology, but obviously at the same time the technology is useless without the data.
Yep.
So my question is, how can we incentivize individuals to release data to build these more exhaustive and large data sets to obviously generate more insights from a larger exhaustive collection?
It's a great question. And you are referring to individuals sharing their data, right? Yeah. So this is an area of active discussion, including even paying people for their data, because of course people do monetize this data when it's aggregated. There is an initiative called the Blue Button Initiative in the US that is at least giving access to a certain set of people the ability to upload their data and share it. One of the things that I think makes this harder, and I think has slowed down progress, is, I have to be careful with what I say, there's a real focus on patient data privacy, and there's a good reason for that. In the US, it's called HIPAA, and so organizations, institutions are very fearful of any sort of data leak or any inappropriate sharing of data, as they should be, and as our company is extremely careful about that. But there's nothing that really stops individuals from just simply sharing their data. And there's been a few pioneering efforts like the George Church effort, the 1,000 Genomes effort, where people just put their data out there. I don't think there's a solution to it yet, but incentives are known to work. Money is known to work. It causes people to do things. So I would like to see some sort of grassroots movement forming. So O'Reilly Media, that's really big into grassroots movements and such, they were a few years ago trying to sort of initiate more of an effort around this, and I don't know that really got off the ground, and I think it's partly tied up with just the HIPAA laws that seem to be getting more strict rather than less. But if you solve it, call me, please, or if you have ideas, we're very interested in it.
All right, so currently I'm aware that implementation of tests for biomarkers at the one gene level or even a panel of genes is highly problematic. Like standardizations of sample prep, analysis, interpretation, et cetera, is lacking. FDA recognized drugs and biomarkers don't even have standardized tests. They're in-house tested, so it can be different results, different hospitals. And add to that, different regulations, US versus Europe. These drugs are going to benefit everybody. So, and also regulatory and reimbursement uncertainties around these tests. So I know that these are big problems. So my question is, if GNS relies on genomic testing, and say even for preterm, you're coming up with a few genes there, but you're still going to have to test for those biomarkers at these sites. Yep. Isn't that an added layer of complication at this point? And can you comment on the infrastructure needed to implement it reliably and at the population level?
Yeah, that's a great question. I mean, it's always the rubber meeting the road is always the key with these really new innovative approaches. And and it does also come down to, how does one want to deliver this kind of knowledge? How does one want to monetize it? And so we have a choice of, do we want to go down the molecular diagnostics path like Genomic Health or like some of these other companies where you're doing clinical trials to really prove the efficacy of this, which also means it takes a lot of money. There's a lot of, for every Genomic Health, which is a company in the Bay Area that developed a test for breast cancer to determine whether or not a woman post-surgical resection should be given chemotherapy or not. And they set a new price point for diagnostic tests at $3,500. There's many kind of failed companies that came after them because they couldn't get through the regulatory hurdles, they couldn't get through the reimbursement hurdles. Where we sit, because we sell both to health insurance companies and to makers of diagnostic tests and of drugs, we live a somewhat schizophrenic life, because on the one hand, we're hearing the payers belly aching about these new drug companies and new diagnostics that are costing all this money and there's not enough proof and blah, blah, blah. And then we hear on the other side from the drug makers and diagnostic makers that say, oh, those payers, they're evil people and they don't want to cover anything. They just want to save money and let patients die. So, the strategy we've taken at GNS is to be very focused on not just simply improving outcomes, but simultaneously improving outcomes and lowering costs. And so we are going to be marketing some of our new tests as really decision support software versus a molecular diagnostic test. So there's other companies that have been through that path, like Foundation Medicine, where they really focused on the decision support side, where they're not telling a doctor that, okay, this drug for this patient because of this mutation. Now, they're putting out a list of results for the doctor to still make that choice, but I think it is pretty straightforward. It's a great question, and it's not a trivial challenge for anyone, including our company.
I'm afraid the clock has intervened. I have to say a great thanks to you, Colin, and to Peter Chow White for coming up with this fantastic and I think exciting session. And I commend you all to follow up on this kind of research. It's clearly critical for so many, both in the Pacific Northwest, but also I think in our lower mainland area. I do have a presentation. I think Joseph has as a token for you, and I'll just let him explain what it is.
To the front here. So on behalf of myself, all the students in the colloquium, and the President's Office from Simon Fraser, I'd like to thank you for your talk today. I'd like to present you with a talking stick carved by Coast Salish artist Jim Yelton. This particular talking stick is the Raven, who is the trickster, and it also represents democracy and free thought, which obviously is very fitting for your talk today. So thank you very much.
Oh, thank you. This is awesome. Yeah, appreciate it. Thank you all. This was a lot of fun.
Great talk. I was even checking my notes. We had a startup company in the year 2000. We were working with the payer organizations in the States for healthcare fraud detection. And it was interesting because we were dealing with